For this chapter 9, we will look at the foundation failures. I will talk about the complexity of the foundation versus the superstructure, for example. And we will also look into the causes of possible foundation failures. So foundations, they are designed to satisfy at least two main criteria. The first criteria is that the structure must be having adequate stability, or meaning that the structure do not collapse, okay, when the foundation is designed properly, okay. Once you have the superstructure that's built on top of the foundation, the load from the superstructure can be supported by the foundation and then spread out to the soil. It doesn't collapse. But not only do you want the structure not collapsing, the settlement should also be within a certain allowable value. Because if the structure does not collapse but settle a lot over the next few years, for example, then the building will also suffer a lot of service-related problems. So the settlement should also be tolerable with respect to the structure. And normally we are talking about the total settlement to be less than, say, 25 mm, for example. Okay, right? So the foundation, we need to satisfy two criteria, okay, stability and acceptable settlement. If the structure is stable but start to suffer from excessive settlement, typically you start to see a lot of cracks forming, okay, and the cracks often is in a diagonal manner. Diagonal because the settlement is uneven. We call it differential settlement. That is, some places settle more than other places, so there is a difference in the settlement, right? Also, you can see here the diagonal crack forming. Okay, so another example, okay, you can see quite a white crack forming at the top here, okay, because this part here is settling more, okay, than this part. Okay, and extreme cases, okay, the building actually is toppling to one side, yeah, okay, so you can see, right? Also, the building is not going to be usable, it's an unsafe building, okay. Even infrastructures like the bridges can also suffer from excessive settlement, okay, and as a result, you will not be able to use, okay, the road, yeah, it will be unsafe. Foundations are complex. There are several reasons or factors that contribute to the complexity of the foundation when you compare to, for example, the superstructure of the building, right? In the superstructure of the building, the main elements like the columns, the beams, and the slabs, okay, in the design and construction processes, they are all man-made materials. It can be structural steel, it can be precast concrete, it can be cast in situ concrete, but all these are man-made materials. So quality control of all these material can be strictly enforced, right, for all these man-made material for above structures, okay. So degree of uncertainty of these materials will be minimized because you can enforce quality control, right. Quality control is easier to implement for the main elements above structure, above ground. For foundations, the foundational elements, be it concrete or steel, will need to interact with the ground because they are directly in contact with the ground. And normally the characteristics of the ground is that it is non-uniform in the makeup, okay. There will be a variation in the engineering properties, okay, and the behavior is complex compared to the above ground structure. So even for a project site, the ground strength may vary from one location to another location, right? And if you have some foundation, for example, board pile, okay, part of the construction process is taking place under the ground where it is not being seen by any person, okay. So lack of visibility and the access, it will hamper the quality control. So that's why foundation is more complicated. Also, in addition, okay, the settlement, okay, of the soil will also take time to occur. It doesn't occur immediately. If it's a consolidation settlement, it will take a very long time. That will further increase the complexity of the foundation design, right? So distribution of forces and the loads can also affect the deformation of the soil, yeah. So there could be examples of, for example, the down drag on the piles because it is suffering from this negative skin friction, okay, right? Redistribution of the pile load because of the deformation of the pile raft or the pile cap, okay, yeah. Or another example is the application of horizontal loads on piles, okay, due to the surcharge loading of the ground nearby. Yeah. Also, all this increases the complexity of the foundation. Let's look at some common causes of foundation failure. The first one is lack of technology. Yeah. So foundation may fail due to the lack of technology. So that means that the state of technology which is available to the profession as a whole is not adequate to cope with the problem on hand. There's a possibility. Another possibility that is more common is inadequate site investigation. Right? So it could be due to ignorance, okay, lack of expertise, or pressure to save costs. Because typically a site investigation costs around 3% of a project. So if you can imagine a project cost of $100 million, cost, then site investigation actually is taking around 3 million. So if you can save 50%, so that is another 1.5 million that you are saving, right? So two shortcomings of site investigation could be the depth of investigation is not sufficient. That means your this bore log is not deep enough, for example, or the wrong type of in situ test or the wrong type of laboratory test was specified. So you do not get the representative data for you to do the design. Design inadequacy could also be a problem that lead to foundation failures. Okay, it includes the wrong choice of foundation type or piling system, inadequate depth or size of the foundation, right? And it may be because certain adverse ground condition, that means a lousy ground condition, they were not detected because the investigation happened to miss it completely, right? Or maybe because the condition was misjudged. It was thought to be okay, but actually it's not okay. And sometimes it could be due to inability to account for all the forces arising from the deformation, the effects of the time, or the groundwater level. There could be construction inadequacy. For example, some of the common construction shortcomings could include setting out errors for the footing or the piles. That means the piles and the footings, they are not at the right location. Insufficient penetration of driven or board piles. That means the piles are not installed at the correct depth. Defective concrete in the footings or the piles. Damage to the pile shaft during the driving. Hole collapse in a board pile. Soft toe in a board pile or damaged toe in the driven piles. Deflection of the driven piles. Bending of the driven piles. Right. So for pile foundation, normally we will do a static load test. Okay, that will be the most reliable technique for assessing the performance of the single pile. So such load testing should be started early in the project to verify the design and the construction adequacy of the piles. Lack of design input during the construction could also be another problem, because design input is critical during the construction stage. So because of the inability to detect in advance all possible significant properties and conditions of the ground, the designer has to make some assumptions during the design stage. These assumptions may need to be changed upon the confirmation of the ground condition, as there's more time to do the further stage 2 site investigation, or when the construction is ongoing and they discover that the ground condition is not the same. So in addition, supervision of the foundation construction should preferably be carried out by the designer, so that vital design input is provided to refine or amend the design where necessary. The following 4 undesirable trends and practices can give rise to foundation problems, and let's look into all of them in a bit of the detail. The first one is the factor of safety. So in many countries, the practice of foundation, are governed by relevant codes of practice. So the required safety factors are clearly spelled out in the code. So owing to competition, there is a tendency to adopt structural factors of safety for piles that are on the low side. So this is manifested in an unrealistically high permissible stress in the steel and concrete piles, the latter including both driven and the board pile. So the factor of safety of a pile should reflect all the uncertainties associated with the underground construction, right? Also, the structural factor of safety for piles should be significantly higher than that for a structural column. So the problem is that, okay, from a owner point of view, a lower factor of safety will mean that they don't need to spend so much money to put in the stronger foundation. And they are not responsible if the foundation fails. It is the designer and the builders that are responsible if the foundation fails. So that's why they may not be so keen to spend so much money, and they try to get the designers and the builders to adopt a lower factor of safety. And on the other hand, the designers and the builders, they are not really responsible for the overall budget of the project. So they don't really need to prioritize on the project budget, but they are responsible for the safety, so they will have a higher factor of safety. So it is different priorities from the different parties, and sometimes things can get out of hand, where you have too low a factor of safety that's adopted, and that can increase the cost of foundation problem or foundation failure. Another problem is a lump sum contract. So occasionally this form of contract is adopted for foundation construction, but it should be avoided where possible. The reason is that the client wants to fix the limit of his financial commitment and pass the financial risk of the variation to the contractor. However, such a step has wide implications which are not appreciated by the client. This is because at the tender stage, usually very difficult to quantify all the technical and financial risk in the foundation construction. So in difficult ground, the real foundation cost of construction can actually exceed the estimated cost by 50% or more. And end up, the contractor may not have the money to carry out the work, so he's going to have problem trying to do a good quality work. And if the work is bad quality, then you can get possible foundation failures. Another potential problem or trend is practicing beyond one's competency. Because no professional is competent in all fields, okay, and everyone will have his limits, okay. So it is the professional responsibility to recognize the limits of their professional competency and practice accordingly. So the client can help by evaluating the track records before appointing the engineer to carry out the design or the construction. Lastly is the pressure of time and money. So there have been cases where insufficient time was allowed for design, tender, or construction. That will increase the risk of mistakes or even blunders going undetected. Sometimes the client takes an excessive amount of time to decide, thereby leaving very little time left for the project. Inadequate budget or over-eagerness on the part of the client to save costs runs an even higher risk of failure. For example, in the historic Tandem Dam failure in USA in 1976, it was found that the pressure of cost budget constraint led to adoption of certain design features in the dam foundation which contributed to the failure.